equals 1 minus 2x over x plus 3. Very good. So then we know now that x equals -3 is the vertical asymptote. And when we determine the limit, as x approaches infinity, remember, please always arrange everything in the correct order, which is the descending order. And then we factor out limit as x approaches infinity, x. It happens that both have the same degree. So it's 1 plus 3 over x, and this one is -2 plus 1 over x. We simplify, of course. These are going to 0, so the answer is -2. So y equals -2 is a horizontal asymptote, and x equals -3 is the vertical asymptote. Awesome. Okay, so we want to go back to the book, and I would like us to look at a word problem. Where are you guys? I'm losing you here. Okay, I found you. So let's talk about the average cost, any of these. If you remember, a while back we talked about the average cost as being the cost over x. So let's say in 53, we have c of x equals 3x squared plus 80. And the average cost is c of x divided by x. So they want us to find c bar, or c of x over x. It's both are the same thing. We're not going to graph it, the average cost, but I want us to find, we can with the graphing calculator, of course, but find the slant asymptote. So this is what I would like. And interpret its significance. Fine. Okay, so first of all, x is in thousands of dollars, so we cannot really talk about negative x, because x is, I'm sorry, the cost is in thousand, of course, but x is computers or units, right? Or whatever they do. So we can graph, but if we graph, when we use the graphing calculator, we have to start at 0, right? We cannot go to -10. Okay, so let's analyze this. Remember what we do when we have a average cost like this. How do I simplify this function? Because it's possible. And why is it possible? Because the denominator is what? What did we say when we looked at these functions? We can simplify them because the denominator has only one what? How do we call this? One what? It's okay if you're wrong. Just let's this is a very important terminology. So what is this? How do we call this? How do we call just x? Or 5x? Or 5x cubed? What are these? Or x alone? One what? Anyone remembers?
A coefficient?
The coefficient is this one. Very good.
Oh.
It's okay.
Variable?
We call it term. One term. So 5x minus 3 is 2 terms. And I won't be able to do what I'm going to do here. So this is the coefficient, and this is a term. So the whole thing is a term, and this is the coefficient. Awesome. So tell me whatever you're thinking so we can correct it and move on and learn. So because it's one term, what did we do when we addressed this before? And also differentiating it and so on and so forth. What did we do when the denominator is just one term? Anyone remembers? How did we address this to simplify it? Because I cannot simplify x with x. That's not allowed. But we did something to simplify it. What was it? Anyone remembers? What?
Divide.
Separate it. So we separate into 3x squared over x plus 80 over x. Anyone remembers this? Remember doing this? Can anyone confirm? Anyone? No one?
So you multiply straight across? Oh, no.
No. So anyone remembers doing from here, this step, applying this step? It's not done, but anyone remembers applying this step or procedure? When we talked about the average cost, average profit, average revenue. No one remembers doing this? Separating into two fractions? It's okay, just say yes or no.
Not really. Here's a refresher.
Okay, good. So then we can simplify now. So this is 3x. Now I can simplify. And this fraction I cannot simplify. So notice that what just happened here, this is a very convenient situation. Very convenient. Because I know exactly what the slant asymptote is. How do I know it has a slant asymptote? Degree 2 at the top, degree 1 at the bottom. 2 over 1. And now the slant asymptote is y equals. Can anyone give us an idea what you think? What you're thinking?
3x.
Exactly. So this, because this approaches 0 when x approaches infinity. Indeed, just the quotient, just the quotient. The remainder over the divisor will always go to 0. That's why only the quotient is the slant asymptote. And now they're asking us to graph. We don't really need to do that, but I would like to graph it so I can put a slant asymptote so you can see that the function, the slant asymptote is also a line like this, like the previous one, because it has a positive leading coefficient. If it were by chance y equals negative 3x, I would have graphed it like this. But if it's positive 3x, I have to graph it like this, and which means that the function will approach infinity here and negative infinity here, which is not possible because it's cost over units. But I'm going to graph the whole thing. So let's just look quickly at the calculator right here. So remember, you have to put in the slant asymptote. The calculator doesn't know to put it in. So this is 3x squared plus 80. Close the parenthesis. And yes, now we can divide just by x because x is one term. I don't have to put any parentheses. And the slant asymptote has to be 3x. I should adjust the viewing window, but I'm going to leave it alone only because I'm just going to use the standard viewing window and see what happens. Only because we should adjust it from 0 because x is number of units, but it's okay. So we're going to graph the whole thing. It may not even appear at all. Yeah, that's possible because
Put 30 instead of 3x.
I did. That's horrible. But the graph of 3x squared plus 80 over x should have appeared. Unless it's completely out of range. So I have the slant asymptote, but I don't have the function. So the function should be up here somewhere. So these sides mean nothing because we're talking about cost and we're talking about units. So the second quadrant, the third quadrant, and the fourth quadrant don't mean anything for this scenario. So I have to work on the first quadrant to see the function. Okay, fine. So from 0 to, I have no idea, I'm going to put 60 with a scale of 10. And y minimum, 0, of course. I'm only interested in the first quadrant. Y maximum, I have no idea. I'm going to put maybe 100 with a scale of 20. So let's see what happens. So the graph of the function, first of all, we know that there is a vertical asymptote at 0, comes to a minimum, and then approaches infinity, following the slant asymptote. Very good. Okay, moving on. I'd like to continue now with applications of optimization. There is nothing I can say about it, just work on different problems. So we have here 2 scenarios. Let me just change the page. I want the page to be 314. Oh, pi, 314. Okay. So in this new section, so the book is ready. In this next section, which is 3.4, we're going to look at something called optimization. And this is my page 4. So 3.4, optimization. Basically, we are talking about max-min again in applications. Before we do that, I would like to look at a particular example, something like this. So this is a function f of x. Notice that I don't have arrows here. It starts here and it ends here. What do you think this point represents? What does it represent?
The minimum.
Absolute, yes. So this is a relative or local minimum. But also, for this function, this is the smallest y value. So this is also called absolute. Sometimes called global. They're the same. Minimum. Now, why is it relative? Because remember, we can show the function on both sides. And the function values are larger than this particular one. Here, I cannot show the open interval. The function does not exist on this side. So this cannot be a relative. This cannot be a relative or local. But it is the largest possible. So this is an absolute max for this function, not relative. Not relative. It cannot be a relative or local, cannot be at the endpoints of the interval. What about this point? This point is nothing. I cannot show the open interval, so it cannot be relative. It's not the smallest ever, so it cannot be absolute minimum. It's not the largest ever, so it cannot be the absolute maximum. So this point is nothing. So this is our first application. So let's take a look and choose an example. So here we are asked, find the absolute max and minimum values of each function over the indicated interval and indicate the x values at which they occur. So why not look at 4, for example? What do you think this point is? Is this point anything?
Nothing.
Nothing. It's at the endpoint of the interval. It cannot be relative, and it's not the smallest or the largest. Nothing. Very good. What about this point? In other words, 2, 2. What about this point?
Absolute.
Absolute minimum. Can it be relative?
No.
No, because it's at the endpoint of the interval. Awesome. What about this point? Kind of hard to read. I'm going to say roughly 0.5, 4.2. What is this point right here where I put the mouse?
Relative max.
It's a relative max as well as
Absolute.
as well as the absolute. Awesome. Great job. Okay, perfect. So we have other graphs again, easy to read. But now let's look at an example. The interval is given to us. So the function now, although we know that this is a polynomial defined from negative infinity to infinity, no, we have to use what they're giving us. They're giving us negative 1, 3. So let's choose any function you want and determine the absolute max, absolute min. And we'll identify also the local max, local min. Which function would you like to work with? No preference? I will choose 15 then. So we have f of x equals x to the third minus x to the fourth. The interval is negative 1, 1. In other words, the world for this function is just negative 1, 1. Let me see.